Hello again. This is video lecture 10.5, and the topic of discussion is Chapter 10, Section 7, in which we're going to introduce a new version of Newton's second law. Certainly a very helpful and powerful tool in studying motion, and we're going to introduce a version of Newton's second law that we can apply to this chapter, Chapter 10, where we have a rigid body rotating about a fixed axis. We want Newton's second law for rotational motion. That's what it's called. Okay? I'm going to just state it, what it is, and then I'll motivate it with a little bit of a kind of a thought experiment. So first, let's just state Newton's second law for rotation. Basically, we've got a rigid body rotating about a fixed axis. We want to be able to predict how it's going to rotate with time. What's going to happen in the future with this rotating object? And Newton's second law, the original version we learned, was very helpful in predicting the future motion of a particle. Let me remind you of that. I doubt if I really need to. But the linear motion, remember, is also called translational motion for a particle. And I'll write it in the way most of the textbooks do. Net force equals mass times acceleration. Old friend. Vector equation, though. F net and A are vectors with components and so forth. What's the rotational version of that is what we want to know. What is the correct form of Newton's second law to use when you've got a rigid body rotating about an axis? We'll call this Newton's second law for rotational motion. I'm just going to argue by analogy. It's not a proof. I'm just trying to make it plausible. But what I'm going to do is take the translational version of Newton's second law, F net equals ma, and replace each of the linear quantities in that equation with its rotational cousin or analog or version. So for example, the rotational version of net force is net torque. Remember that symbol there? Is a Greek lowercase tau. And so that means net torque. Replace net force with net torque. Replace mass with rotational inertia, I. That's the rotational analog of mass, which remember, mass is a measure of inertia. Now we have rotational inertia. And linear acceleration A becomes angular acceleration alpha. That's the rotational version of Newton's second law. You must find the net torque about the specified axis of rotation. Let me emphasize, we have to know what the axis of rotation is because torque is calculated relative to an axis of rotation. We also need the rotational inertia about that same axis of rotation because remember, rotational inertia is also calculated relative to an axis of rotation. So what I want to emphasize is that net torque and rotational inertia in this new equation must be calculated about the same axis of rotation. And what this says is that the net torque equals the rotational inertia times the angular acceleration, which you can, if you wish, write as angular acceleration equals net torque divided by rotational inertia. And then it's a cause and effect relationship, just like the translational version of Newton's second law is. What you get out is an angular acceleration when you have rotation. What causes an angular acceleration? A net torque. And then you have to divide by rotational inertia to get alpha. So that's one way to write the rotational version of Newton's second law. We will now use that in the rest of Chapter 10 and as needed in Chapter 11 whenever we want to make a prediction about the rotational motion of a rigid body. But just so that you don't think I'm pulling this result out of nowhere, let me make it plausible, this tau net equals I alpha, by looking at a kind of a little experimental setup. And in this setup, the drawing is over here on the right, we have a more or less a particle. It's drawn to look like a kind of tiny disk that's connected by a rigid but very light, negligible mass rod to an axis of rotation pinned there at the origin, axis O. And so that disk, and this is a horizontal frictionless surface, you're looking down from above, that disk can then rotate in a circular arc of radius r about the axis of rotation O. And let's say what I want to do is to get the disk to rotate counterclockwise and speed up. I'm going to contrive that by adding my own applied force. I'm going to pull on that disk in that direction with an applied force F. And I contend that that will cause the disk to rotate counterclockwise and speed up. Now the picture shows that that force can be divided into two components. One component along the rod, that would be the radial component, F radial, and one component perpendicular to the rod, which is tangent to the circle. We'll label that component F tangential. Note that that's not the only force on that disk. It would have an F grav that would be going straight down into the screen. Remember, this is a horizontal frictionless surface. It'd have an F normal coming straight up out of the screen. Those two balance. There's also a force on the disk due to the rod itself, which would be down this way, and such that the net radial force would be towards the center. That I must have. I know from my earlier study of circular motion. But the important force for what we want to study is this component of my applied force, the tangential component. That, I contend, is the key component of the forces acting on the disk. It's the component that's going to cause the disk to speed up as it moves in a circle. So what I'm going to do to motivate this new version of Newton's second law is study this situation. And I'm going to start by applying Newton's second law for the tangential components. For linear motion, A tangential equals F net tangential over m. Because I'm really thinking of that disk as basically being a particle. It's clearly not a very big disk relative to the radius r. It's not a bad assumption to assume it's just a particle. And apply the old-fashioned version of Newton's second law to describe its linear acceleration, and I'm focusing on the tangential component because that's the interesting one. But there's only one tangential component, that tangential component of my applied force. So I'm just going to label that Ft over m. Let me multiply both sides by m, and I get a pretty simple little formula. F tangential equals the mass of the disk times A tangential. It's tangential linear acceleration. All right, we'll number that equation 1. Now let's calculate the torque on the disk about the axis through the origin O. That's where the axis is, clearly specified here. Remember, the symbol for torque is the Greek lowercase tau, and that there are really three equivalent, mathematically equivalent ways to calculate torque. You could take force times moment arm, F times r perp, or r times the perpendicular component of the force. And that turns out to be the one I'm going to use in this case. Because the perpendicular component of the force component that's perpendicular to r, is F tangential. In other words, that's a right angle right there. And so I'm just going to take the length of that rod, r, times F tangential. That's the torque. And it's a counterclockwise torque, so it's positive. We learned how to deal with that in the previous video lecture. Now I'm going to substitute for F tangential from equation 1, right there in the torque equation. Okay, let's see what we get. Let's continue with the calculation over here. So the torque on the disk about point O is r times F tangential which is mass times tangential linear acceleration. Now I need another idea from a little earlier in chapter 10, relating linear kinematic variables to rotational kinematic variables. The tangential acceleration of our disk can be written as its radius of its circular path times the angular acceleration alpha. A tangential equals r alpha. Chapter 10, section 3. So I'm going to substitute that in for the A tangential and see what the torque formula looks like. R times m times r times alpha. Well, let's just do some grouping. M times r squared times alpha. But if that's a particle, which was what I'm thinking of the disk as a particle, then there's a simple formula for the rotational inertia of the particle as it rotates about an axis. It's mass times the radius squared. So that expression, mr squared, is the rotational inertia. And I have that the torque on that system equals its rotational inertia times the angular acceleration. In other words, the new version of rotational motion that I just described before. All I wanted to do was take a particular situation, so this is hardly a proof, and apply some physics ideas to that particular situation and show that this new equation comes out. And then I will just state that this new equation will be used generally to study the rotation of any rigid body about a fixed axis of rotation. Net torque equals rotational inertia times angular acceleration. And that's what we will now use. Okay? For rotational dynamics. Now I just have a few tips, things to watch out for about using this new equation. Okay? All right. First of all, just like in linear motion, the force you talk about in F equals ma must be F net, must be the net force. The torque you talk about in the rotational version must be the net torque on the body. You must take all the torques that are acting about the given axis and add them up to get the total. In our case, with that disk, F tangential times r was the only torque. Next, both the net torque and the rotational inertia must be calculated about the same axis of rotation, because they both depend upon where the axis is. So they must be calculated about the same axis so that the two sides of the expression remain equal. Next tip. Net torque and alpha are vector quantities, even though we don't write the arrows. And all we have to do to denote the directions is give a plus sign or a minus sign for tau net and alpha. But this new version of the second law requires that tau net and alpha be in the same direction. Newton's new version of his second law requires that. All right, so now we're just going to spend the rest of this video applying this new result, and then in class we're going to do the same, more application. So I'm going to have us do some practice with Newton's second law of rotation. And I'm going to have us look at a rigid body that rotates, a socket wrench. And we're just going to focus on the handle of a socket wrench, okay? And the picture down here is a photograph of a socket wrench handle, and it's meant to be pivoted or rotated about an axis at one end. And then you pull on the other end, okay, to get something to rotate. So that's a socket wrench handle, okay? And we're going to assume that it's currently being held horizontally in a vertical plane. So this photograph is vertical, and we're going to hold it up so that it's in a vertical plane, but it's being held horizontally in a vertical plane. Okay? And the left end is fixed such that the handle can rotate in a vertical plane. So there's the axis of rotation at the left end. I'm just going to take it to be exactly at the left end to make the geometry easier. Turns out three forces act on the handle. the force due to gravity, because that handle has some mass, which we will assume acts at the handle's center of mass. An applied force, which is going to act at the right end of the stick at an angle theta, although I'm going to change that to a phi. So if you'll allow me, I'm going to do that right now. Phi to the horizontal, phi. And there's a force due to the hinge at the left end. So we're going to model this handle the way a physicist would. A uniform stick with mass evenly distributed. Mass m, length L, where the mass is 0.5 kilograms. And I'm going to show you a Wiley Plus animation of the handle, okay, in just a minute. And that animation shows two of these three forces acting on the handle, F grav and the applied force. It also plots what the handle's angular acceleration alpha would be as a function of the angle phi of our applied force at that end. See, this is our applied force. It's got a certain magnitude. We don't know what it is, but it's got a certain magnitude. And the animation allows us to vary this angle phi. So we're down there holding that right end of the stick with that applied force F, and we can adjust the angle at which we apply this force. Okay? So that's an object that rotates. Let's do some analysis on it. First, let me show you the animation I referred to on Wiley Plus. Okay? So here you're looking at a vertical plane. Vertically up is upward there in the picture. You can see the horizontal stick. It's being held horizontally. That represents the socket wrench handle. You can see the axis of rotation is that large dot at the left end. And you see two forces acting on the handle. The one in the middle that points straight down is F grav. The gravitational force on the handle, assumed to act at its center of mass, which is right in its center. And then the other force is our applied force, F, we'll just call it, okay? At angle phi. All right, now, the slider tells me that right now, that angle phi is set at 30 degrees. Okay, because you can see it up there, I think, at the top, right? You can see that. Yep, that the slider tells me that the angle phi of the applied force is 30 degrees. There's also a graph of the angular acceleration in radians per second squared that handle would have as a function of phi. And you can see the red dot on the graph. That corresponds to what angle we've set at, 30 degrees. And notice that the red dot shows me that the angular acceleration is 0 if the angle of our applied force phi is 30 degrees. That's a situation we call rotational equilibrium. That means that the stick will stay there at rest if my applied force at the end there is at a phi of 30 degrees. If I change my applied force, angle, phi, to be anything other than 30 degrees, the graph shows me that the angular acceleration is not 0. That means in that case, that handle, that stick, would rotate and speed up. And it would rotate either clockwise or counterclockwise, depending exactly on what the phi is. Okay? So that's what's going on here. Note, by the way, that if I click on this, it'll also show me the force on the left end of the stick from the hinge, as long as we're in this equilibrium configuration. And that's it. And you may be thinking this. If so, good intuition. If you add up those three force vectors, you'll get 0 when you're in equilibrium. But I'm going to take away that hinge force because that's not going to be an important player in our calculations. And hopefully you'll be able to see why. All right, let me now go back to, I'll be going back and forth between the animation and our note screen here. Let me sorry, got this here and I don't want it. Okay, no. Okay, there we go. Let me read to you what question A says. The plot in the graphic, as we talked about, shows that when phi is 30 degrees, the angular acceleration, so when phi is 30 degrees, the angular acceleration of the alpha of the handle equals 0. It will be in equilibrium, rotational equilibrium. It will not rotate. It will stay at rest. We say the handle is in equilibrium in this situation. Let's use this information and an analysis based on Newton's second law for rotational motion to determine a value for the magnitude of that applied force at the end. Okay, that's our first task. All right. So we are told to apply the rotational version of Newton's second law. That's our starting point. All right, let me draw my own picture. There's the hinge at the left end of the stick. There's the uniform stick, length L. Okay, let's draw the forces acting on the stick. There is our applied force, F, that makes the angle phi with the horizontal. And then the center of mass of the uniform stick would be at its geometric center, L over 2 from the left end. And the F grav of the stick would act vertically downward at that point. Now, yes, there's that hinge force on the stick at the left end, but notice that that hinge force acts right where the axis of rotation is, right? And I'm going to label that axis A for axis. And note, any force that is applied exactly where the axis of rotation is produces zero torque because it has no moment arm, and you need a moment arm with a force to get a torque. So I don't need to worry about the force on the stick from the hinge at the left end. So back over here in my statement of Newton's second law rotational version, I'm going to add one more little thing. The net torque is going to be calculated about the axis A. And the rotational inertia, therefore, must also be calculated about the axis A. But we're in equilibrium here. That means no acceleration of any kind, including angular. So the alpha equals 0. So then Newton tells me that the net torque on the stick about axis A must equal 0. Notice this is only when phi has that somewhat magical value of 30 degrees. All right, so I contend then that there are going to be a total of 2 torques on the stick about point A. One will be a positive torque, one will be a negative torque, and their total must equal 0. Let's get a symbolic expression for those torques one by one. Let's do the gravitational torque first. Tau sub g, the torque due to F grav. Okay, I'm going to leave a little bit of space for a plus or minus sign, and I'm going to use the form of moment arm times magnitude of force, where I have to make sure I get the moment arm calculated correctly. So the line of action of that force is just an extension of that arrow. Remember, that's important. That's called the line of action. Then the moment arm is perpendicular distance from the axis of rotation to the line of action. So it goes perpendicularly to hit the line of action. There's your R perp for F grav. Of course, it's just along the stick. That's easy enough. And it's exactly half the length. All right, so I know what the R perp then is. It's L over 2. Now, here's a question. Is this a positive torque or a negative torque? I would want to see this in your work. So here you got to look at the scenario, the situation. You got to look at where the hinge is, the axis of rotation. You got to look at the force, F grav only, and look which way it's pulling. Ignore the applied force. Which way would the stick rotate given the axis and the way F grav is pointing? It would rotate clockwise, yes? And clockwise torques are negative. So I have to insert a negative sign in front. Now I put in that this is negative L over 2 mg, right? Because magnitude of F grav is mg. There's the symbolic expression for gravitational torque. Next, let's get a symbolic expression for the torque from the applied force. I'll label that tau sub F. I'll leave room for the sign, SIGN. Then I'll get the appropriate moment arm times the magnitude of the force. But be careful. Let me go back up to my picture and get rid of some things. Not quite everything. I'm even going to get rid of F grav arrow for now. Okay, because I'm only focusing on F applied. So, to get the moment arm, first draw the line of action of the force, so extend it. This time I have to go this way. Then, moment arm is perpendicular distance from the axis of rotation to the line of action. So I've got to go from A and hit that line of action at 90 degrees. Just do your best to get the sketch to look about right. That's our perp for the applied force, right? Every force has its own moment arm. Now you have to do a little bit of trig and geometry. If this angle right here, which we've said, the angle of the applied force relative to the horizontal is phi, then this angle over here is also phi. Vertical angles are congruent. Now I want you to look at this right triangle. The hypotenuse is L, there's an acute angle phi, and the moment arm is opposite to phi. So I should be able to deduce, in this case, that R perp, the moment arm for the applied force, is L sine phi. Now what's the sign of this torque? Which way would this force cause the stick to rotate? Look at the hinge, the axis, look at the force and which way it's pulling. Ignore F grav. Which way would the stick rotate? Answer is counterclockwise. And counterclockwise torques are positive, so plus sign. So altogether we have L sine phi, and let me just write F for the magnitude of the applied force. Okay? There are the two torques. So now what I'll do is I'll get the symbolic expression for the net torque about axis A. Just add these two symbolic results. Negative L over 2 mg plus L sine phi F. But use the fact that I already argued that the net torque about axis A must equal 0. So then all I have to do is solve for F, the magnitude of that applied force. Right? Just a matter of algebra. Note I can divide both sides by L, and the L factor goes away. I don't need to know how long the stick, the handle is. So I get F equals mg over 2 sine phi. And let's just plug in numbers. I am told the mass was 0.5 kilograms. G is 9.8. I'm going to express the unit as Newton per kilogram. over 2 times, the sine has to be, the angle phi has to be 30 degrees if we're in equilibrium. That's the only value of phi that's acceptable if you're going to have an alpha equal to 0. And so when I plug that into my calculator, I get F equals 4.9 newtons, half of 9.8 in fact. That's the magnitude of that applied force, no matter what angle phi it's at. Okay, we applied Newton's second law for rotational motion in the situation where there happened to be 0 rotational motion. And so then Newton tells me in that case that the net torque about the axis must equal 0. I used that fact to solve for something, the magnitude of that applied force. Now let's look at B. What is the rotational inertia I of this handle about the axis at the left end, where A is? This will be a symbolic expression in terms of M and L. So no numbers, symbols. Get that up a bit. Okay, we'll see if that's enough room for doing part B. So we are to find the rotational inertia of the stick about point A. Okay, this is going to be a very common calculation for the rest of this chapter and in chapter 11. I need to find the rotational inertia of an object, simple shape, a uniform rod or stick, but I have to be clear where the axis is, and the axis is not through the center of mass, right? The axis is through at the left end of the stick. How am I supposed to find this rotational inertia? Answer, parallel axis theorem. I said we were going to use this a lot. And the parallel axis theorem says, you want to know the rotational inertia for an axis that's displaced from the center of mass? See, up here, our center of mass is right in the middle, but we don't have an axis through there. The axis is through the left end. You want to know the rotational inertia about an axis displaced from the center of mass, such in this case? It's given by the rotational inertia for an axis through the center of mass, plus more. The entire mass of the thing, whatever it is, times what the book calls h squared. H is some kind of distance, and you have to be clear what this distance is. Let me draw another picture so we don't have too much clutter. There's the axis A. There's the center of mass. We're comparing the rotational inertia for an axis about A to the rotational inertia for an axis through the center of mass. H is simply the distance between those two axes. In this case, H is that distance, which clearly in our case is half the length of the stick. Yes, L over 2. So that's what we're going to use for H. So let's write that. M times L over 2 quantity squared. Now, what do we do next with this expression? This is the parallel axis theorem. Let's write that so it's very clear what we're using. Well, I need to know what ICOM is, because I got to add that to MH squared. Well, that's good news, because the shape here is just a rod. And if the axis is to be considered through the center of mass, I can use that table, that figure 10.5.1, that has those different entries for different shapes and different axes. And I look up a rod or stick of a given mass and length with the axis through its center. And it will tell you the rotational inertia. That's what ICOM is. It's 1/12 times the mass times the total length squared. And that's what we're going to substitute for ICOM. So we have 1/12 ml squared plus this is ml squared over 4. Now let's just add these two symbolically. ml squared over 12 by getting a common denominator. We'll multiply the second term, numerator and denominator, by 3. That gives me a 12 downstairs. Now I have a common denominator, so I can add the numerators. ml squared plus 3ml squared is 4ml squared. Divided by the common denominator, 12, and that simplifies to ml squared over 3. That is the answer for part B. That is the rotational inertia of that uniform stick about an axis through, actually it'll apply to either end. We use the parallel axis theorem. We will do that a lot. But we've done all it's asked to do in part B. So now, let's go to part C. Part C says, find a symbolic expression for the handle's angular acceleration alpha, and that means for arbitrary phi, between 0 and 90, okay? And then use the information from the plot in the graphic to determine the length of the handle L. Okay, so now it's just saying apply Newton's second law, rotational version, for arbitrary phi. So I start with alpha equals tau net about point A over rotational inertia about point A. That's what I'm applying now. And the alpha is not necessarily 0 because the phi is not necessarily limited to 30-degree value. Now, let's not do too much work, but let's be careful that what we put down is correct. For the net torque, the beautiful thing about having symbolic expressions in part A, right here, for tau grav, for tau grav and tau f, is those symbolic expressions can be applied for any phi. And they're perfectly appropriate symbolic expressions for tau grav and tau f. So I'm just going to write those symbolic expressions because I need the net torque. So I need tau grav plus tau f. I'm going to write it like this. FL sine phi, that's tau f, and minus mgl over 2, tau grav. Okay, I use those symbolic expressions, and now I can put in any phi I want. Now for the denominator, I need the answer from part B. ml squared over 3. Now I can divide numerator and denominator by a factor of L, and I get rid of almost all the L's, but not all. Do your algebra carefully. Okay, that simplifies to now this. 3 goes upstairs, parentheses. F sine phi minus mg over 2. All over ml. That's a nice symbolic expression for alpha as a function of phi. Because I'm thinking of phi as a variable now. It can be anything between 0 and 90. Right there. That's a nice little symbolic expression for alpha as a function of phi. And in fact, that's the formula that was used to make the plot we see in this animation. That plot of alpha in radians per second squared versus phi in degrees. It was made precisely using this formula. Substituting the m, the f magnitude, and an L value that they haven't told us. That's what we have to find, isn't it? So let's do one more step then. Let's take that symbolic expression that was used to make that graph and rearrange it and solve for L, because that's the thing they ask us to find. So now let me go back to my notes. And let's solve that little formula we just derived for L. Just do a little bit of algebra. Cross multiply. You get L equals 3 times F sine phi minus mg over 2 over m alpha. And we're going to use that with our graph to get L. All we got to do is pick a point off the graph. We've done these kinds of problems before. But pick a point that makes things easy, or easier, or easy, as easy as we can. So let's look at that graph and pick a point that makes it easy. Well, we might incline to leave it right there at phi equals 30 degrees. That seems pretty easy, doesn't it? We've got a problem, though, if we do that, because then the alpha is 0, and we got a 0 in the denominator. So, no, let's not do that. It just means that phi, you can't use this equation to solve for L. It doesn't mean L is infinity. Let's pick a different phi. Well, let's still pick something that's as easy as it can be. How about this? When phi equals 0 degrees, according to the plot, you've got to be able to read the graph, alpha equals negative 30 radians per second squared. That graph is telling me that if I were to make the angle of the applied force 0, like that, and lift it like that, that rod, that disk, would start to rotate with an angular acceleration of negative 30 radians per second squared, and the negative tells me that the motion would be clockwise. Let's use that fact along with our equation to get a value for L. So that means we substitute phi equals 0 and alpha equals negative 30. Let's see what we get for L. 3 times F, hey, we just found F, 4.90 newtons, times the sine of phi, 0, minus m, 0.5 kilograms, times g, 9.80 newtons per kilogram, divided by 2. That's in the numerator. And in the denominator, I have m, 0.5 kilograms, and alpha, careful, negative 30 radian per second squared. Well, actually, the sine of 0 is 0. That term goes away. So you can see it better. And the numerator then is negative. But there's a negative in the denominator, so if you were worried I was going to get a negative value for L, you'll see if you do your calculator work carefully, you do not get a negative value for L. I'll give you the answer with 2 sig figs. You get L equals 0.49 meters, almost a half a meter. All right? All right, that's a typical, that would be like an interactive exercise kind of YB plus problem, where we had to apply Newton's second law for rotational motion. We're also going to do an example problem in class where we apply Newton's second law for rotational motion. So that's all for this video.